In the previous lecture, we discussed about the complete pH curve, and we also came up with an equation which was used to generate that complete pH curve, and that equation was a complicated kind of equation. And we also discussed some approximations that we are going to use in further discussion. But when we talk about pH, especially with reference to biologically important systems, it becomes very important. Because for biologically important molecules, for example, proteins, nucleic acids, pH becomes very important. We will discuss later that how pH can affect their conformation and hence their properties. So therefore, while preparing a solution of biologically important systems in laboratory, we prepare a solution which is called buffer. Therefore, it becomes very important to understand what is a buffer. And the connection of buffer is with its resistance to change the pH of a solution upon addition of a small amount of an acid or a base. And that is why pH becomes very important. Another question is that what salts or an acid should be chosen to obtain a solution of a particular value of pH. For example, if we want to prepare a solution of pH 5 or pH 7 or pH 9 or pH 12, what salt and what acid should be taken? These are important questions, and we will address these questions in today's lecture. Let us start discussing about pH curve for titration of weak acid with a strong base. Now what we have is, at stoichiometric point, the hydronium ions in solution stem from influence of OH ions on autoprotolysis equilibrium, and OH ions are produced by Bronsted equilibrium. We are talking about this expression, that is the negatively charged ions, for example the hydroxide ions, and OH ions, you see, which are also produced by the autoprotolysis of water, and the action of A ions on water upon acceptance of proton, because A ion is a Bronsted base, it will accept a proton and result into the formation of OH minus ion. And therefore, these will influence the stoichiometric point. If I write equilibrium constant for this particular reaction, it will be activity of HA into activity of hydroxide ion over activity of A minus, taking activity of water to be 1, and you convert these into molar concentrations, you get this kind of expression. You have molar concentration of HA, molar concentration of OH minus, and molar concentration of A minus. Treat it as within the brackets. Now what happens after sufficient addition of acid, that is well past the stoichiometric point, pH is controlled by excess base present. Please look at this statement very carefully. After sufficient addition of acid, well past the stoichiometric point, pH is controlled by excess base present. How? I can write this expression that H3O is equal to Kw divided by OH minus ion. Even if I write this by using autoprotolysis of water, the hydronium ion concentration is approximately given by the autoprotolysis constant of water divided by hydroxide ion. So, it is the amount of OH ion, if it is in excess, that is going to control the pH of the solution, because H3O plus will be modified accordingly. Then again, if I take logarithm on both sides and set minus log H3O plus as pH, and OH ion concentration will result into POH, and then use pH plus POH is equal to pKw. I am skipping a step over here. Why I am doing it? Because we have discussed these things many times, and eventually one will get this relation, which pH is equal to pKw plus log B prime, where B is the amount of the base that is present in solution. So, that is what I was trying to comment upon, that the pH of the solution is controlled by the excess base which is present in the solution. And let us talk about the pH curve for titration of weak acid with a strong base. This is the type of curve that we discussed in the previous lecture that one will obtain when you titrate a weak acid with a strong base. Let us try to identify different regions. Let us say here we start with, this is purely weak acid, no base added, and when you keep on adding base, the horizontal axis represents volume of titrant and the vertical axis is pH, and this is how the pH changes, and this represents equivalence point. Also pay attention to the various equations which are written over here. This equation we have just derived, the relationship between pH is equal to pKw plus log B. When you have excess base, that is what we just discussed, if there is an excess base, pH will be controlled by excess base, and you are talking about this region. You are starting with pure acid. So, let us see pure acid. And since we are talking about a weak acid, I will write the acidity constant is equal to activity of H3O plus into activity of A minus into divided by activity of HA. That is how we write the ionization constant or acidity constant for a weak acid. And let me write again, Ka is equal to, if the acid is weak and initially there is no base present, then both these have to be equivalent, because the source of A minus is also, so HA, and the source of H3O plus is also HA, and you are not talking about the contribution from autoprotolysis of water. So, if I equate these two activities, I can write this as H3O plus raised to the power 2, and this I will retain as A0 because this is hardly dissociated. Acid is hardly ionized. We can ignore the extent of ionization and write this approximately as the initial concentration. So, activity of H3O plus square is equal to acidity constant into A0, and this is same as this equation H3O plus is equal to square root of acidity constant into A0. And now I can take logarithm log activity of H3O is equal to half log Ka plus half log A0. And the next step will be, you take a negative sign on both sides, you multiply by -1, convert this to pH, convert this to pK, and this remains then as -1/2 log A0. And that is what, if we look at the figure now, that initially that is what is the equation. pH is equal to half pK A minus half log A0. pH is given by this expression. And the pH is modified as you keep on adding alkali, and halfway to stoichiometric point, this equation we also derived, that when A prime is equal to S, when the concentration of acid and concentration of salt are equivalent, pH is equal to pKa, and that is what is indicated over here. At the midpoint, halfway to the stoichiometric point, pH is equal to pKa. And you see the region of the pH change is reasonably flat around pKa. This flat region has a lot of significance. That means a slight addition of an acid or a slight addition for a base is not going to change pH significantly, because you see within this circled region, this is a flat region and the pH of the solution does not change when you add a little more amount of the titrant, and that is what is called the buffer action. What is a buffer? It's a substance which does not allow the change of pH upon addition of small amount of an acid or a base. And for what pH value it should be used, it depends on the pKa. That means we should choose a substance and the region, that is wherever it has a value of pKa plus minus 1, pKa plus minus 1, that range can be used to be selected as the substance for preparing a specific pH. For example, if I want to prepare a solution of pH 7, then I should pick up a salt or an acid. The pKa of the acid should be, let us say, 7. If the pKa is 7, then the pH can be 7 plus minus 1. So, in other words, if I want to prepare a solution of pH 7, then I should use an acid or the salt of that acid where the acidity constant is within a range of plus minus 1 of that value. So, therefore, if the pKa is 6, then I can use that acid and its salt to prepare a buffer of a solution of pH from 6 to 8. For a pKa of 7, the pH can be 6 to 8, comfortably can be used, and that lies in this flat region. So please do remember this, that whenever we want to prepare a solution of specific pH, it should fall within plus minus 1 range of the pKa value of that acid. Let us go back to the figure now. You continue adding alkali and you see beyond this region, it is very sharply changing, and we will soon derive this equation at the equivalence point. And then further addition will give rise to another saturation, that is the pH becomes constant over there, almost constant over there, unless there is another ionization further happening. And this equation we also derived. Now let us try to derive this kind of equation, this equation which is at the equivalence point. Find an approximate expression for the pH at the stoichiometric point of the titration of weak acid with a strong base. Calculate its value for the titration of 25 ml of 1 molar HClO with 0.1 molar NaOH. Again we are talking about weak acid and a strong base. And as usual, since we are talking about weak acid and a strong base, we will again use those approximations. We are talking about weak acid and we are talking about strong base. So whatever is A minus we are talking about anion of the weak acid, we can equate that equal to S if I use S as the concentration of the salt which is formed as a product. And whatever is the concentration of HA and whatever is the amount of H3O plus it produces, this I will equate equal to, let me write these as the concentrations, OH ion. These are the two approximations that I am going to use. So therefore, equilibrium constant is equal to OH minus square over S. And from this I can get OH is equal to OH minus is equal to S into K square root from this equation. Okay. K, which is activity of HA into activity of hydroxide ion over activity of A minus can be written as activity of HA into activity of hydroxide ion, and let me divide and multiply by activity of hydronium ion and then combine these two. These two multiplication is equal to Kw, autoprotolysis constant of water. This is equal to Kw by Ka, because this is Kw and Ka, reciprocal of Ka is A into A of HA over A minus into A H3O plus. This is the activities. A is written as activities. From this, if I substitute Kw by Ka for K into this expression, I get expression for OH, and from this I can easily get POH by taking logarithms, and pH plus POH is equal to pKw. Therefore, I can express this equation in the form of pH, and this is the expression that we were looking for. And once you substitute the values of pKa of the acid and we substitute pKw, which is 14 at 25 degrees centigrade, and the concentration of salt form will be 0.05, and the final answer can be obtained as 10.1. So, please try to solve this in a detailed way by yourself, but this method describes how pH can be obtained at the stoichiometric point, and this is the expression to be used at the stoichiometric point, and that I showed in the previous figure. The equivalence point, that is the concentration of salt, can be calculated from the given information, and that please try yourself. Now, buffers and indicators. I have discussed about the need of buffers. A buffer is a substance which resists the changes in pH upon addition of a small amount of acid and small amount of base. Indicator, as the name suggests, indicates the occurrence of the equivalence point. Let us discuss details. This is Henderson-Hasselbach equation, and this equation suggests that the slow variation of pH in the immediate vicinity of S equal to A prime is the basis of buffer action. Remember that flat region. And buffer action is the ability of a solution to oppose changes in pH, as I just discussed. The mathematical basis of buffer action, what is the mathematical basis? Is the logarithmic dependence of this ratio of acid to salt concentration. The logarithmic dependence is the mathematical basis, and whereas the physical basis is abundant supply of A minus ions, because salt is there and this A minus can remove any hydronium ion by additional strong acid. That is when small amount of an acid is added, and alternatively or vice versa, that is numerous HA molecules can supply H3O plus ions which can react with strong base that is added. So, both these statements are examples of the Le-Chatelier principle, application of Le-Chatelier's principle. All right. The rapid change of pH near stoichiometric point in a titration is the basis of indicator detection. We will discuss more about that. An acid-base indicator is generally a water-soluble, weakly acidic organic molecule, and that organic molecule should be able to exist in an acid form. I write as HIN, and conjugate base where proton is donated, and I write as IN minus form, and both these occur in different colors. The proton transfer equilibria will be this. You have an acidic form of the indicator HIN. It will donate its proton, form hydronium ion, and will have IN minus, and these two will have different colors. That is, before the titration it will have color specific to this, after the titration it will have color specific to this. Let us write down equilibrium constant for this, Kin I write, which is activity of hydronium ion into activity of indicator in the negatively charged form over activity of the indicator in weakly acidic form, and take the logarithm and express this logarithm ratio of log HIN by IN minus as PKIN minus pH. This relation can be obtained by manipulation of this. And now I can use this relation for further discussion. According to this relation, when pH is less than PKIN, the overall value is positive. That means the indicator is predominantly in the acidic form and has its corresponding color. And when pH is higher than PKIN, then this overall it is negative. That means indicator is predominantly in its basic form and will have its corresponding color. At the end point, you have pH is equal to PKIN. All right. That is why it is commented over here that at stoichiometric point of an acid base titration, pH changes sharply, and if pH passes through PKIN, that is when it passes through this equality, there is a pronounced color change. Thus, end point will coincide with the stoichiometric point of titration. And I am sure that this reminds you of the methyl orange or phenolphthalein, which was used as indicators in the acid base titrations during your school level laboratory classes. And today's discussion describes that why the color of the indicator changes. It is just the change in the state of ionization, that each ionized state has a different color. So, what we discussed in today's lecture is about a very important concept, and that is buffering action. What is a buffer? I am again repeating that in biologically important systems, buffers play a huge role, because several biologically important molecules have their specific activity at a particular pH value, and therefore maintaining that pH becomes very important, and therefore selection of the acids and its combination with the salts, which will give us that particular pH value, becomes very important. And I hope today's discussion helps in deciding that which molecules should be taken, which acid, which salt should be taken to prepare pH of the desired pH value. Thank you very much.